So now we have to think about torque. So we're just about to start our other rotational stuff. So again, torque by definition, okay, is R cross F. Now what that really translates into is torque equals the radius, how far you are away, multiplied by the force, okay, times by the sine of the angle, theta. Okay, now if this is our point of rotation here, and we're pushing here, here's our theta. So we can take our radius, the distance we are from the point of rotation, we put that there, have the force, put there, and then the sine might end there, so you can see sine theta, the theta that is in between there. So essentially what we're doing is we're just getting the perpendicular, okay, component of the force, because that's what could cause rotation. The parallel part or anti-parallel part cannot. So that's why we take the vector cross product. Now there's lots of examples of torque and statics and things like that in your notes. You can take a look at my summary notes on that. But I'm just going to do one again. The most common one is the flagpole. So what if I have a person standing here and I've got a string and then we have a board. Okay, so we of course will then have the force of gravity of this person downwards. The board will be right in the middle of it. Okay, and then we have this tension force going upwards like this. And what if we want to find this tension force here? So let me label that Ft here. Okay, and this of course is our point of rotation. So the first condition of statics is the sum of all forces equals 0. The second condition of static equilibrium is the sum of all torques equals 0. Okay, so I'm going to find the gravity force of this situation here. Okay, so let's say this person here, okay, has a weight of 600 newtons. So I'm just going to take a negative 600. Okay, and I'm going to multiply that by the distance to the point of rotation. Well, for 10 from here, and that's 22, so that's going to be times 12. Okay, that says 12 there. And I would put sine of 90, but I know that that's 1, so I'm not going to worry about that. Now it's negative torque because this person's going to rotate this beam in a clockwise direction. Therefore, that's negative torque. Now the next one is going to be the beam. Let's say the beam weighs 50 newtons. So I'm at minus 50. And I got to multiply that by 11. That's the distance to the point of rotation. Okay, so 11 from here to the point of rotation. And that's going to be negative torque again. Now I'm going to go plus, okay, force tension. Okay, and I'm going to multiply that by, let's see, looks like it's 22 total away from it. Okay, and then I'm going to multiply that by sine of whatever the angle theta is. And I just have one unknown, and that'll be my force tension. Now the sum of all forces in the y direction also equals 0. That's the second condition, okay, for equilibrium. So we're going to have a force in this direction upwards. Let's call that P. We're going to have a force tension in the y direction upwards. That's force tension sine theta. So if I was to write this expression, I would have P upwards, a plus force tension sine theta. We will already know that value because we solved for force tension, minus mg, that all equals 0. Now in the x direction, we have a tension force pushing this way. It's going to be pushing this way. Okay, that's going to be force tension cosine theta. Okay, cosine theta. And then we're going to have a P in this direction also. Okay. Okay, let's call that Q. Now, of course, this really is a force in the y direction. This is really a force in the x direction. I'm just giving it variables for it to be called. So I'm just calling that Q right now. So you can call it whatever you want. You can call it this. You can call this one Py and this one Px if you'd like to. But anyways, these two would oppose each other, add up to 0. So you have a Q in this direction, a force tension minus force tension cosine theta that direction. That also equals 0. So the sum of all torques equals 0. The sum of all forces equals 0. Those are the conditions of equilibrium. Save.